This is a demonstration of the single cycle computer push and pop instructions. So start viciLab, run from the library the push pop SCC configuration file. It's a viciLab application file. It will take several moments before you're prompted to enter your viciLogic username and password. This will configure a remote system on chip device with the single cycle processor configured. Select the widget at the bottom if it doesn't appear automatically, and you will open a series of tabs that are specific to this push pop configuration of the single cycle computer. Open an assembly program in the individual instructions folder and the push pop program. There are certain bits being set in registers, and there are a block of push and pop instructions and an end instruction. Assemble the program. Syntax is correct, so this transfer to program memory is enabled. The IDE appears. On this side we have the register bank 0 to 7, special function registers 0 to 7 and 8 to 15. The data and stack memory, these are relevant in this application for push and pop. The instructions from instruction 0 to instruction 10 or A, these are the 16-bit instruction values. Over here is the hardware that's active for this particular instruction, the set BR instruction, which is the first instruction here. Another video explains setting, clearing, inverting bits, etc. But what this does is puts patterns 1, 2 and 3 into registers 1, 2 and 3 in turn. So I'm going to step the instruction 4 times, and you'll see that as a result there are values 1, 2 and 3 in registers 3. I won't look at the previous hardware configurations for those instructions, there in other videos. I've now 3 push instructions and 3 pop. I'm pushing register 1 onto the stack. So the address for the stack is the stack pointer. So the stack pointer is stored in the special function register bank as special function register 3, 0, 1, 2, 3. It's 0 in this particular instance, it's 0 initially. And that address is fed into what is the data and stack controller. And the configuration of this block, the hardware that's active, puts the address 0 through to the data and stack address as the value 0. It also is writing to the stack, and it's also putting a value of data into here. And if I follow this back, this is coming from a register array, which is this register array. And the address of the register, the source address inside the operand fetch, is 1. And that is the bits 2 to 0 fields in the instruction. They define the source address. There really should be a blue star lit beside the clear beside the 1 here to show that register 1 is coming from here being brought back, and that's the value 1 because it was defined over here with data value 1, and therefore that's pushed into the data going into the stack memory, and on the next clock address 0 has data value 1 written into it. So I'll step here, and this will now take the value 1 and put it into the stack memory, and this will be seen over here in this window. Address 0 now has a data value of 1, and notice that the stack pointer value has incremented to 1. So I can go to the data and stack controller, which is this block, and you'll see that there's a lot more functionality within that block. And also I can look at the stack pointer counter, which is a counter that has 12 bits, and the counter could be incremented or decremented. Currently the count value is 1. So let me just go back and reset the program again to the first instruction and step forward 4 instructions back to the push instruction. So this is the picture which was seen before, but now I'm going to go straight to the data and stack controller for this instruction and show you for all of the hardware that's there. What's happening is register B, which has the data value of 1, is being selected through more hardware within this device to give the data value 1 into the stack. And the address from here comes from the stack pointer and through the path which is shown here with the star. The star illustrates the paths through the muxes that are active. And the memory write signal, which is asserted by the instruction decoder for this particular push instruction, gives rise to the assertion of DS write. If I go to the stack pointer now, and you can see the value 0 here, looking inside that red box, I have the registers for the stack pointer. The current value is 0, and if I follow the active labeled paths, the stars, you'll see that the stack pointer is incrementing through, and on the next clock edge, active clock edge, the stack pointer will increment. And that happened before, but I just didn't see that. Why did that happen? It's because the signal increment stack pointer was asserted by the instruction decoder for this push instruction, and that controlled this multiplexer, which selected the current value through the incrementer and through, and then disregarded what's happening in the rest of the hardware. If I go back to the IDE again, you'll see now that that value in the stack will go to 1. And now I'm pushing the value in register 2 onto the stack. The value in register 2 is value 2. That, for the same reason, is the data going into the stack. The address of the stack has now incremented to 1, so now I'm going to write automatically to address 1. And write as asserted as before. So the instruction decoder has asserted memory write and increment stack pointer. Meanwhile, down here, the program counter is incrementing. It's currently 5, it will go to 6. 5 is the current instruction. Now the pointer in data stack memory is to address 1, as is shown back here. And when I step the next instruction, this will go to the value in R2, which is 2. Now I push the value in R3, which is the value 3, into the stack data. It's going to the stack address 2, which is coming from the incremented stack pointer. And the picture is the same as before, except some of the parameters have changed. For example, the source data, it's now register 3, and the opcode for the instruction is 0110-000, and this is the instruction 6003 is the instruction, these bits. I can step again, and now all 3 of those values, 1, 2, 3, are written to the stack. And the stack pointer is now pointing to address 3, 0, 1, 2, 3 in the stack. Now I'm doing a pop to register 5. So this diagram has changed. The destination register is this register, and the star illustrates that register 5 is the destination register. The current stack pointer is at 3, but in the stack controller there is a decrement component which generates the previous stack written to, stack address written to, and that provides the data out of the stack and through here. There's lots of options in the write back block. In this particular case, the data is coming from the stack through to here. It's not coming from some other part of the process, and it will write to here. Notice that the instruction decoder now has decrement stack pointer asserted because it will now decrement the value 3 to 2. The stack manages the current address and the pointer. Current. Also select data and stack out is a signal that's asserted because it has to select the path from data and stack through in the write back block. And the register that's been written or out is the register 5, which is the destination in the instruction, and it's shown by the star here. And register write is also asserted. So there are a different set of signals in the instruction decoder that are asserted. The 100 for the destination register is part of the instruction up here, and the opcode is different from the previous. And again, the program counter is just incrementing. So if I step the instruction, register 5 will take on the last data value written to the stack, which was the value 123 from register 3. So we pop from the stack in the reverse order that are pushed. And if I toggle 2 more times, you'll see the second and third pop happening to different registers, and the value 2 and 1 will be popped onto registers 6 and 7 respectively. And the stack pointer is now back at 0 again, so there's no relevant information in the stack. Even though there's data there, it has been pushed and popped, so effectively that data is not going to be used for anything else. And then we're on an end instruction here where nothing happens, nothing is written to registers, nothing is written to data or stack memory. The only signal that's asserted is the end program signal, which holds the current program count, which is A, at A, no matter how many times we step the program. That's the end of the presentation.